Yes, I wanted to read this book. This is the hard book to read. It's the book everybody needs to read, but no one wants to tackle it. It's too much. Too much, man. This shit too much. If you've read this book, you can make $1 million a year. If you've read and understood this book, it's $1 million a year. There's even a book that Bill Gates wrote the epilogue to, where he said, if you've read this book cover to cover, call me, get a job at Microsoft. Very few people really finish this stuff. This is CUDA. It's worse than AI. It's AI under the hood. I get sick just looking at the first few pages. Programming massively parallel processors. A hands-on approach. There's also a video series. Yeah, right? Imagine thinking CUDA isn't a moat. The 18 people who have read this at Microsoft really want to help NVIDIA and AMD out. Want to read with me? You want me to read it out loud to you guys? I don't know, I ain't reading it out loud. But I know somebody who will.
We are proud to introduce to you the third edition of Programming Massively Parallel Processes, a hands-on approach.
Mass-market computing systems that combine multi-core queues and many-thread GPUs have brought terascale computing to laptops and petascale computing to clusters.
Multi-core CPUs and many-thread GPUs. You kind of messed that one up, Samuel. I have to fix your dictionary.
Armed with such computing power, we are at the dawn of pervasive use of computational experiments for science, engineering, health, and business disciplines.
Many will be able to achieve breakthroughs in their disciplines using computational experiments that are of unprecedented level of scale, accuracy, controllability, and observability. This book provides a critical ingredient for the vision, teaching parallel programming to millions of graduate and undergraduate students so that computational thinking and parallel programming skills will be as pervasive as calculus.
We've gotten rid of those hallucinations in our new version, coming soon.
Since the second edition came out in 2012, we've received numerous comments from our readers and instructors, readers and instructors. Many told us about the existing features they value. Others gave us ideas about how we should expand its contents to make the book even more valuable.
Our new version sounds much better, actually. It's like totally lifelike.
Furthermore, the hardware and software technology for heterogeneous parallel computing has advanced tremendously since then.
In the hardware arena, 2 more generations of GPU computing architectures, Maxwell and Pascal, have been introduced since the first edition.
Oh, I love you.
In the software domain, CUDA 6.0 through CUDA 8.0 have allowed programmers to access the new hardware features of Maxwell and Pascal. New algorithms have also been developed. Accordingly, we added 5 new chapters and completely rewrote more than half of the existing chapters.
I can kind of do it in parallel. This is what the API is for.
Broadly speaking, we aim for 3 major improvements in the 3rd edition while preserving the most valued features of the first 2 editions. The improvements are 1, adding new Chapter 9 parallel patterns, parallel histogram, computation histogram. Chapter 11, parallel patterns, merge sort, and Chapter 12, parallel patterns, graph search, that introduce frequently used parallel algorithm patterns. 2, adding new Chapter 16 application case study, machine learning on deep learning as an application case study. And 3, adding a chapter to clarify the evolution of advanced features of CUDA.
I like how she goes 3, 2.
These additions are designed to further enrich the learning experience of our readers. As we made these improvements, we preserved the features of the previous editions that contributed to the book's popularity. We kept the book as concise as possible. While it is tempting to keep adding material, we wanted to minimize the number of pages a reader needs to go through in order to learn all the key concepts.
We should just make one button to press and it turns your PDF.
We accomplished this by moving some of the 2nd edition chapters into appendices. Second, we have kept our explanations as intuitive as possible. While it is tempting to formalize some of the concepts, especially when we cover basic parallel algorithms, we have strived to keep all our explanations intuitive and practical.
You kind of need an Adobe plugin, right, for PDFs?
The target audience of this book are the many graduate and undergraduate students from all science and engineering disciplines, where computational thinking and parallel programming skills are needed to achieve breakthroughs. We assume that the reader has at least some basic C programming experience. We especially target computational scientists in fields such as computational financing, data analytics, cognitive computing, mechanical engineering, civil engineering, electrical engineering, physics, chemistry, astronomy, and geography, all of whom use computation to further their field of research. These scientists are both experts in their domain as well as programmers. The book takes the approach of teaching parallel programming by building up an intuitive understanding of the techniques. We use CUDA-C, parallel programming environment that is supported on NVIDIA GPUs. There are nearly 1 billion of these processors in the hands of consumers and professionals, and more than 400,000 programs. The applications that you develop as part of the learning experience will be used and run by a very large user community. How to use the book, we would like to offer some of our experience in teaching courses with this book. Since 2006, we have taught multiple types of courses in 1 semester format and in 1 week intensive format. The original Oil C498 course has become a permanent course known as SC408 or C483 of the University of Illinois at Urbana-Champaign. We started to write up some early chapters of this book when we offered SC498 the second time. The first 4 chapters were also tested in an MI class taught by Nicholas Pinto in spring 2009. Since then, we have used the book for numerous offerings of X408, as well as the Coursera Heterogeneous Parallel Programming course and the VSA and Pump Summer Schools. 3-phased approach in ESEF 408. The lectures and programming assignments are balanced with each other and organized into 3 phases. Phase 1, 1 lecture based on Chapter 2, Data Parallel Computing, is dedicated to teaching the basic CUDA memory threading model, the CUDA extensions to the C language, and the basic programming debugging tools.
Debugging tools.
After the lecture, students can write a simple vector addition code in a couple of hours. This is followed by a series of 4 to 6 lectures that give students the conceptual understanding of the CUDA memory model, the CUDA thread execution model, GPU hardware performance features, and modern computer system architecture.
Where's the goal?
These lectures are based on Chapter 3, Scalable Parallel Execution, Chapter 4, Preface XVI Memory and Data Locality, and Chapter 5, Performance of their matrix multiplication codes increases by about 10 times through this period.
Wow.
Phase 2. A series of lectures cover floating point considerations in parallel computing and common data parallel programming patterns needed to develop a high-performance parallel application. These lectures are based on Chapter 7, Parallel Patterns, Convolution, Chapter 8, Parallel Patterns, Prefix Sum, Chapter 9, Parallel Patterns, Parallel Histogram Computation. Chapter 10, Parallel Patterns, Sparse Matrix Computation. Chapter 11, Parallel Patterns.
Merge, sort, and Chapter 12, Parallel Patterns.
Graph search. The students complete assignments on convolution, vector reduction, prefix sum, histogram, sparse matrix vector multiplication, merge, sort, and graph search through this period.
Did she turn trans briefly?
We typically leave 2 or 3 of the more advanced patterns for a graduate level course. Phase 3. Once the students have established solid CUDA programming skills, the remaining lectures cover application case studies, computational thinking, a broader range of parallel execution models, and parallel programming principles. These lectures are based on Chapter 13, CUDA Dynamic Parallelism, Chapter 14, Application Case Study, Non-Cartesian Magnetic Resonance Imaging. Chapter 15, Application Case Study, Molecular Visualization and Analysis. Chapter 16, Application Case Study, Machine Chapter 17, Parallel Programming and Computational Thinking. Chapter 18, Programming a Heterogeneous Computing Cluster. Chapter 19, Parallel Programming with OpenAC, and Chapter 20, more on CUDA and Graphics Processing Unit Computing. The voice and video recordings of these lectures are available as part of the Illinois VIDIA GPU Team Kit.
What is that? That sounds interesting. Sounds like something I should have. They got a whole syllabus for NVIDIA at a university. That's fucking crazy. Think about that. Think about how crazy that is. Yeah, we're going to learn NVIDIA in college.
Tying it all together, the final project.
Yeah, stay after class so I can whoop your ass. Wait, the Squeep's a chick?
While the lectures, labs, and chapters of this book help lay the intellectual foundation for the students, what brings the learning experience together is the final project, which is so important to the full semester course that it is prominently positioned in the course and
commands nearly 2 months.
It incorporates
focus.
5 innovative aspects: mentoring, workshop, clinic, final report, and symposium. While much of the information about the final project is available in the Illinois and NVIDIA GPU Teaching Kit, we would like to offer the thinking that was behind the design of these aspects. Students are encouraged to base their final projects on problems that represent current challenges in the research community. To seed the process, the instructors should recruit several computational science research groups to propose problems and serve as mentors. The mentors are asked to contribute a 1 to 2 page project specification sheet that briefly describes the significance of the application. What the mentor would like to accomplish with the student teams on the application. On the application, the technical skills, particular type of math, physics, and chemistry courses required to XVI preface, understand, and work on the application. And a list of web and traditional resources that students can draw upon for technical background, general information, and building blocks, along with specific URLs or FTP paths to particular implementations. These project specification sheets also provide students with learning experiences in defining their own research projects later in their careers. Several examples are available in the Illinois NVIDIA GPU Teaching Kit. Students are also encouraged to contact their potential mentors during their project selection process. Once the students and the mentors agree on a project, They enter into a collaborative relationship featuring frequent consultation and project reporting. We, the instructors, attempt to facilitate the collaborative relationship between students and their mentors, making it a very valuable experience for both mentors and students. The project workshop is the primary vehicle that enables the entire class to contribute to each other's final project. We usually dedicate 6 of the lecture slots to project workshops. The workshops are designed for students' benefit. For example, if a student has identified a project, the workshop serves as a venue to present preliminary thinking, get feedback, and recruit teammates. If a student has not identified a project, she can simply attend the presentations, participate in the discussions, and join one of the project teams.
Makes me want to go back to school.
Students are not graded during the workshops in order to keep the atmosphere non-threatening and to enable them to focus on a meaningful dialogue with the instructors and teaching assistants and the rest of the class. The workshop schedule is designed for the instructor, SA, and teaching assistants to take some time to provide feedback to the project team so that students can ask questions. Presentations are limited to 10 minutes to provide time for feedback and questions during the class period. This limits the class size to about 24 presenters, assuming 90-minute lecture slots. All presentations are preloaded into AC in order to control the schedule strictly and maximize feedback time. Since not all students present at the workshop, we have been able to accommodate up to 50 students in each class with extra workshop time available as needed. At the University of Illinois, the high demand for S408 has propelled the size of the classes significantly beyond the ideal size for project workshops. At the University of Illinois, the high demand for S408 has propelled the size of the classes significantly beyond the ideal size for project workshops. We will comment on this issue at the end of the section. The instructor must make a commitment to attend all the presentations and to give useful feedback. Students typically need most help in answering the following questions. First, are the projects too big or too small for the amount of time available? Second, is there existing work in the field that the project can benefit from? Third, are the computations being targeted for parallel execution appropriate for the Keto programming model? The design document. Once the students decide on a project and form a team, they are required to submit a design document for the project. This helps them to think through the project steps preface X6 before they jump into it. The ability to do such planning will be important to their later career success. The design document should discuss the background and motivation for the project, application level objectives and potential impact, main features of the end application, an overview of their design and implementation plan, their performance goals, a verification plan and acceptance test, and a project schedule. The teaching assistants hold a project clinic for final project teams during the week before the class symposium. This clinic helps ensure that students are on track and that they have identified the potential roadblocks early in the process. Student teams are asked to come to the clinic with an initial draft of the following 3 versions of their application. The best KPU sequential code in terms of performance, preferably with AVIX and other optimizations that establish a strong serial base of the code for their speed up comparisons, and 2, the best C2A parallel code in terms of performance. This version is the main output of the project.
See the typo? This should be
This version is used by the students to characterize the parallel algorithm overhead in terms of extra computations involved. Student teams are asked to be prepared to discuss the key ideas used in each version of the code, any numerical stability issues, any comparison against previous results on the application, and the potential impact on the field if they achieve tremendous speed up. From our experience, the optimal schedule for the clinic is 1 week before the class symposium. An earlier time typically results in less mature projects and less meaningful sessions. A later time will not give students sufficient time
to revise their projects according to the feedback.
The project report. Students are required to submit a project report on their team's key findings. We recommend a whole day class symposium. During the symposium, students use presentation slots proportional to the size of the teams. During the presentation, the students highlight the best parts of their project report for the benefit of the whole class. The presentation accounts for a significant part of students' grades. Each student must answer questions directed to him, her as individuals, so that different grades can be assigned to individuals in the same team. The symposium is an opportunity for students to learn to produce a concise presentation that motivates their peers to read a full paper. After their presentation, the students also submit a full report on their final project. Class competition. In 2016, the enrollment level of LA 408 far exceeded the level that can be accommodated by the final project process. As a result, we moved from the final project to class competition.